Welcome back. Today we're diving deep into the V engine, and it's built on a pretty wild idea. What if you could get flawless performance by just not asking for new memory while the game's actually running?
Okay, let's kick things off with a question that I'm sure drives every single one of us crazy. You've got the monster rig, the top-of-the-line CPU, and yet you still get those awful micro stutters. Why? What is actually going on under the hood?
Well, the thing is, the root of this problem isn't just some sloppy code. It's way deeper. It's an architectural flaw. The folks behind V-Engine straight up say that the standard ways we manage memory in C++ are, and this is a direct quote, fundamentally broken for making games.
So, what do? They declared war. And their enemy? The memory heap. You know, that big pool of memory that programs are always asking for little bits of? Every single time a game does that during gameplay, it's basically rolling the dice. It introduces chaos, unpredictability, and, lag.
Think about it like this. Every time your game asks for a little piece of memory and then gives it back, it's like tearing a page out of a book. Do that thousands of times, and you're left with a shredded mess. That's heap fragmentation. The system has to waste precious time hunting for a clean, big enough piece. And that hesitation, that's the stutter you feel.
All right, so the V-Engine team drew a line in the sand. They put it right in their official design docs, ADR-009 to be exact. The new rule? No more asking the standard heap for anything during the main game loop. Full stop. It's a radical move, but it's the absolute core of how they get rid of that fragmentation and those random slowdowns.
Okay, so how on earth do you build a game without asking for memory? Well, they have this really clever 3-level strategy. And we're not talking about a small change here. This is a complete rethinking of memory management. It's a kind of high-level engineering you see in massive engines like Frostbite, the one that powers the Battlefield games.
It all comes down to 3 key pieces, all working together perfectly. Each one has a very specific job to do. First, you have static pools. For the really important stuff, like the job system, they just grab 10,000 slots of memory right at the start, before anything happens. So when a new job needs to run, bam, the memory is just there. It's instant. We're talking O1 speed. No searching, no hesitation, just pure, reliable performance. Then, for all the temporary stuff, data that's born and dies within a single frame, they use something called a frame arena. It's a big 16-megabyte chunk of memory. And here's the magic. At the end of the frame, they don't bother cleaning up thousands of little pieces. They just hit a giant reset button. A single pointer gets moved, and the entire 16 megs is considered empty again. It's incredibly efficient.
And what does this get you? Pretty much the holy grail for any real-time application. You get zero fragmentation. You get performance you can count on every single frame. And you seriously cut down on threads tripping over each other trying to get resources.
But look, having a rock-solid memory system is only part of the puzzle. It's the foundation. Now let's see what they build on top of it, because this is where it gets really smart. See, great performance isn't just about raw speed. It's about timing. Most systems are imperative. They're like, do this heavy task right now, and boom, you get a stutter. The engine uses a declarative approach. It lets the developer say, hey, here's a heavy task, do it whenever it makes sense. It completely separates the what from the when.
So for instance, think about a complex AI calculation. Does it really need to run 60 times a second? Probably not. With this system, you can just tell it, hey, run this every 5 frames. Instantly, you've spread that performance cost out, and everything feels way smoother.
Or even better, what about background tasks, like loading the next area of the map? You can schedule those to only run when idle, when the CPU has a spare moment. This is huge. It means background loading will never steal resources from the main action, guaranteeing you stay within that crucial 16.6 millisecond window for a perfect 60 frames per second. And this intelligence goes all the way down to the metal. We're talking about being fully hardware aware. The V-Engine is built to squeeze every last drop of performance out of modern CPUs, like an i7 with its 8 physical cores and 16 logical threads. It knows exactly how the chip works.
This table is brilliant. It shows how the engine is SMT aware. So modern CPUs have physical cores and then logical threads, sort of a way to pretend you have more cores. For brute force jobs like rendering, V-Engine says, great, use all 16 logical threads. Let's get maximum throughput. But for delicate, latency-sensitive stuff like AI, it pins the work directly to the 8 physical cores. Why? To avoid what's called cache contention, basically preventing tasks from stepping on each other's toes inside the CPU's short-term memory. It's a high-end optimization that makes a massive difference for stability. Okay, so we've talked a lot of deep tech stuff, but what does it all mean for you, the player? How does all this intense engineering actually translate into a better game?
Well, it enables things that used to be incredibly difficult, like truly seamless level streaming. As you're running through the world, low-priority jobs are firing off in the background, decompressing the next part of the map. And because they're using that when idle scheduler we just talked about, this all happens without you ever noticing. No loading screens, no hitches, not a single dropped frame.
So, how does this custom solution stack up against the big guns? The team behind V-Engine isn't shy. They're benchmarking themselves against industry leaders, specifically Unity's high-performance DOTS framework. And the numbers are pretty impressive. Thanks to its zero-allocation design and some very clever lock-free programming for its job system, V-Engine can chew through 10,000 events in less than 1.9 milliseconds. That's not just good, that's right up there with the best of the best.
This whole approach, this obsessive focus on architecture, isn't just an academic exercise. It's what the developers themselves call the engineering price we pay for a rock-solid feline adventure. It's all in service of creating an experience that is just flawlessly smooth. And really, it makes you think, doesn't it? What other fundamentally broken ideas are we just accepting as the way things are done in software today? And what could we build if we had the courage to tear them down and start fresh?